Welcome to EDU World Space.
Elements in group 7A in the periodic table are called halogen, and 6A are called chalcogen. What is the most common oxidation state of chalcogens compared to halogens? So group 7A, then 6A, then name is chalcogens. Oh, sorry, this is halogens, and this are chalcogens. So most common oxidation states are represented with OS is -1. This is -2. And B, for each of the following periodic properties, state whether the halogens or chalcogens have larger value. One is atomic radii. Atomic radii. So when you look at the periodic table, the atomic radii decreases across a period, and you're going to get to group 6A before you get to 7A. So the atomic radii for 6A is greater than that for 7A. Okay. The next one is ionic radii. Ionic radii, IR. So how do we come about ionic radii? Ionic radii comes from when we lost electron. So when you lost electron, you form, or when you gain or when you lost an electron, you form an ion. So group 7A and 6A, they have ionic radii when they gain an electron. So the group 7A can gain one electron. So I'll just put that here, 7A. When they take one electron, they form, okay, this will be the best way to do it. Cross this out. So you take 7A, say 7A, and I'll represent it with hex. So you have 7A, you have hex. When it gains an electron, they can only gain one electron because they need one electron to complete their octet configuration. You form hex minus, and then group 6A, they can gain 2 electron, and when they gain 2 electron, they need the 2 electrons to complete their octet configuration. They form X2 minus. So a lot of times when you look at it, the group 7A, of course, if you're considering the same period on the periodic table, so for instance, if we have maybe oxygen 8 and fluorine 9, right? So if oxygen 8 gains 2 electron more, they have the same shell number. Oxygen and fluorine have the same number of shells. Like the outermost shells uh, is the second shell. So they have 2 shells. So if the electron is going into the second shell, then what would determine the size of the 2 would be the number of protons that they have in the nucleus. And of course, the fluorine has more proton in the nucleus than the oxygen. So after you form the, I'm going to take this to the next page for better explanation. So after you form, let's say you have a O8, okay, and it's neutral, and then you put 2 electrons to form O2 minus, okay. The electron configuration for this is 2 6. So the new electron configuration is 2 8 because you had 2 electrons. Now for the fluorine, you have 9, and then you can add just 1 electron to form 9F minus. So the electron configuration for this is 2 7. The electron configuration after the adding of electron is 2 8. Okay. So if you picture it, they both have the same. I'll put the nucleus as this small circle, and inside it you have 8 positive charge, which is a proton. Then you have 2 electron in the first shell and 8 electron in the next shell. Okay, 1, 2, 3, 4, 5, 6, 7, 8. And for fluorine, it's going to be like this. You have 9, and then you have 2 electrons, and then you have 8 electrons as well. 3, 4, 5, 6, 7, 8. Please pardon my drawing. So if this is what is happening, what would determine the size of this two diagrammatic representation is the charge in the nucleus. So here we have a 9 positive, and here we have 8 positive. Just like electrons and protons, they attract each other. So the more the positive charge, the more the attraction, and so that pulls. The more the attraction, the smaller the size, because the positive charge pulls the shell closer to itself, and that decreases the size of the atom. So because of that, the F minus will be smaller than the the O2 minus. So that goes back to what we're doing here. The ionic size of the chalcogens, of the halogens, will be smaller. So the 7A is smaller than the 8A, than the 6A, I mean. Okay. Then the next question says common oxidation states. Okay. First ionization energy. Okay. So the ionization energy now. The first ionization energy. So ionization energy is the energy that's required to remove electron, right? So the general trend is that the ionization energy, when you go from left to right across the periodic table, it increases because size reduced, and there's increase in atomic number as well because you're adding more proton to the nucleus. So the ionization energy of the 7A is greater than the 6A. And then the second ionization energy is the energy that's required to remove the second electron. So if you, let's say you remove the first electron from this, you're going to have 8 whole positive, and this will be 9F positive. So you're trying to remove, well, you will have you have a 5 electron left here, and here you have 6 electron left here. So you're trying to remove the second electron to form a whole 2 positive and F2 positive. Of course, it's still gonna be this will be hard to remove than this, right? Or you can, to have a better understanding, you can look at the electron configuration. So you have a 2s2, 2p3 in this case, and here you have a 2s2 and 2p4. Okay, so it will be harder to remove electron in this case because the p orbital is half filled, and here the p orbital is of course, it's more than half filled because you have the p orbital that looks like this. 1, 2, 3, 4. And here you have one that looks like this. 1, 2, 3. So here you have some repulsion, and that will lead to a decrease in the ionization energy. So the 6A is greater than 7A. Okay, so that's it.